Okay, it is really happy to invite you to this wonderful discussion today on recurrence relation. Recurrence relations coming um, in the third unit of your syllabus, discrete mathematics. Discrete mathematics. Okay, so let me take the topic now. This is what discrete mathematics, and the title is recurrence relations. Recurrence relation. So what is that? Let us discuss about that. Now consider this: a comma a plus d comma a plus 2d a plus 3d dot dot dot. Can you remember this series or progression? We say it is an arithmetic progression. How each terms are progressing here. The first letter is a, the second is a plus d, third one is a plus d plus d, that is a plus 2d, and third one is, or fourth one is a plus d plus d plus d, or a plus 2d plus d, a plus 3d dot dot dot. What is the technique behind this? The initial element is added by the common difference each and every times, and thereby we are getting the next terms. The initial element is added by the difference each and every time, and thus we get this progression, or we can say sequence. This is a technique behind that. Am I correct? Right. So if in a sequence each term is obtained from its previous term, then we call it as a recurrence sequence. We can say recurrence sequence. Now look at that recurrence relation. Now what is this? If a sequence is like this, then we can get a relation like this connected to this. A relation is possible to make such a sequence, and that relation is called recurrence relation. Recursion relations. Okay, now look at that. What is the relation? If a1 equals a and ak plus 1 equals ak plus d, for k is greater than or equal to 1, then we will get this sequence. This sequence will get where a1 is equal to a. Now ak plus 1 equals ak plus d. Let k is equal to 1, you will get a2 equals a1 plus d. We are getting the second terms in the sequence. Now for k equals 2, we will get a 2 plus 1 3, which equals a2 plus d. a2 is what? This one plus d, we will get this a plus 2d. Similarly for k is equal to 4 5 6 dot dot dot, we will get a plus 3d, a plus 4d, like that. So this is the relation which makes this sequence. The sequence is what? Recurrence sequence, I told you. So the relation connecting this recurrence sequence, we call it as a recurrence relation, we say. Now what's the solution of that? Solution is nothing but the sequence which satisfy this recurrence relation is called the solution. Now here an equals a plus n minus 1 into d. For n is equal to 1 2 3, we will get the terms of this particular recurrence relation, recursion relation, that is a comma a plus d plus a plus 2d a plus 3 dot dot dot. Now let us check here. When n is equal to 1, we will get a1 equals a plus 0. When n is equal to 2, a2 equals a plus 2 minus 1. into D, A plus D, second terms we get here, and now you put n is equal to 3, you'll get A plus 2D, A 2 equals A plus if A3 you put here, then A plus 2D, like that. So that's what we are getting here, the sequence. Now we'll have example here for the arithmetic progression. Now suppose the first element is 5, the common difference is 3, then we will have 5 comma 5 plus 3 8, and 8 plus 3 11, like that. So this sequence is a recursion sequence, and where the initial element is A, that equals 5, the common difference is D equals 3. So for this also we can find out a recursion relation like this, where D is equal to, we can take 3 and other things as it is, where A1 is equal to 5. So here A1 is equal to 5, and this equation AK plus 1 equal to AK plus 3. You will get this particular sequence. Therefore this is a solution of this recursion relations as we have here. Similarly here, when A is equal to 2, D equals 5, you'll have 2 comma 2 plus 5 7, 7 plus 5 12, 12 plus 5 17. So again we'll have a recursion relation like this, where A is equal to 5 and AK plus 1 equals AK plus 5 for K greater than or equal to 1. Last one, when A is equal to 1, D is equal to 0. When A1 is equal to A, D is equal to 0, what we'll have for different K, we'll get 1 1 1, and that is what we have here. The second discussion is about geometric progression. We know that AR comma AR squared dot 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 is called a geometric progression. Here also we have an initial amount is multiplied by R many times, that is common ratio, we will get this particular geometric series. So for that, the recursion relation is A1 is equal to A, and AK plus 1 equals R into AK for K is greater than or equal to 1. A1 is equal to A comes here, and then when K equals 2, you'll have A2 equals R into A1. A1 is A, so A into R you will have. That's what you have as a second element here, and same like this dot dot dot, you'll get this geometric progression. So this is the corresponding recursion relation. As we studied before, this gives you the solution for this geometric progression. Okay, solution. These are the examples for geometric progression. 1 into 3, 3 into 3 9, 9 into 3 27, 27 into 3 81 dot dot dot, where the initial element is A and common ratio is R equals 3. Similarly here 5 comma 10 comma 20 comma 40, the initial element is A and the common difference is R is equal to 2. So 5 into 2 10, 10 into 2 20, 20 into 2 40, like that. Similarly we can get this geometric series too. So with that I am coming to the end of this small piece of work based on recursion relations. Thank you very much.